So we'll go ahead and get started. Good morning, good afternoon, depending on where you're coming from. We thank you for coming today. We're very excited to be showcasing this case study, this joint venture between IMR, Renishaw, and Entopology. My name is John Graham. I manage the team of application engineers at Entopology, and I've got the pleasure of introducing everyone here to you today. And this is the order in which we're going to be going. So I'm going to turn things over to Mark Hartnett in just a moment at Irish Manufacturing Research. Our very own Chris Cho at Entopology is going to walk through how this medical device was designed and some of the breakthrough technologies in Entopology. And then finally, Chris Demery at Renishaw will give you an overview of some of the printing capabilities and how they turn this design into a reality. Now, one thing to mention before I turn this over to Mark is that this is really a technology demonstrator that we're showing you today. You know, most of you, if not all of you, understand additive manufacturing is really changing the landscape of how things are not just manufactured, but the approach to design. A lot of breakthrough technologies are coming out on the scene, and all three of our companies are at the forefront of exploring how can we take something like additive and push the bounds, not just in the way things are manufactured, but the way we think about design and where these designs can be used, even something as wild as in the human body. So that's what we're talking about today. So this actual design hasn't been put in a body quite yet, but this is really a demonstrator of the capabilities that I believe are soon going to be coming down the road, and some of them may have already been there. So I want to turn things over to Mark Hartnett now of Irish Manufacturing Research, and he'll walk through what this design was all about and what led them to try to push the bounds and use something like additive manufacturing. Mark, go ahead and take it away.
That's brilliant. Thanks for that, John. Chris, if you can just jump to the next slide, lovely. As John said, my name is Mark. I'm one of the AM researchers out here in IMR, and I'm a specialist looking at design for additive manufacturing. And what we do is we're working on helping industries across Ireland, Europe, and the world adopt new cutting-edge technologies to help them keep competitive manufacturing. So I suppose when we look at the production of any product, be that through a traditional workflow or a additive manufacturing workflow, we start with this ideal design that exists somewhere in the ether. And trailing down from that, we have a number of constraints, first of which being the physical design constraints which are placed on it. And these come from your design team, the existing methodologies that they have that comes from their training and their past experience, their inherent skill, and then the software and the tools they're using to develop their products. Following from that, we all know about the limits which the chosen manufacturing technology places on your product and can often bring it far from the ideal design. And then closely linked with that are the cost constraints that come with trying to produce a component as reliably, as quickly, and as cost effectively as possible. And what these do is these limit the ability of your product to reach that ideal design that existed at the beginning of this workflow. So what additive allows us to do, we have the same ideal design that exists there, but by using new tools, the advanced skill sets, and retraining our designers, we're able to design and develop a product that's much closer to that of the ideal design. The manufacturing limitations that are placed on that by additive manufacturing are much less than those that exist from a traditional manufacturing process. And finally, the cost limitations that come with additive manufacturing are much less constraining. You're able to do a lot more with your process for the same cost compared to a traditional manufacturing process. And this is where that adage of complexity is free comes from. So when we're designing our product, our first goal is to produce our design envelope. And we need to do that for both the process and for our product. So if we look at our process design, we start with a key user requirement. We get through our voice of customer analysis. So the first one is obviously the product has to be designed well for the process which is producing it. So we come up with a number of design solutions which allow us to hit this. So if we take, for example, minimizing the post-processing requirements, there are a number of ways that we can minimize the amount of post-processing we need to do to a product. If we understand what the effect of self-supporting geometry is, the effect of the overhang angle on surface finish, and how we can get away with producing a part without any support geometry, we can produce a much better component with a lot less additional work at the end. So if you take, for example, by producing it with a bullet nose tip, we're able to build it straight onto the build plate, allowing us to produce a part with no support removal. So then we start to come to our product window. And this is where it begins to get really interesting, because our key user requirements are what are going to affect the customer at the end of the day, not what's going to affect us internally. So if we take, for example, improving subsidence management. Subsidence is when the implant itself moves into the bone, gets reabsorbed into the body, and actually starts to present the same and worse symptoms that you're trying to treat in the first place. So we can do that we can improve that through a few ways. We can reduce the stiffness of the device, and we can do that by applying porous structures or other compliant features into the bone. And one of our goals there can be to match the stiffness of the bone which we're going to be in contact with. And we come up with a methodology for measuring whether or not we match that stiffness. So we look at test methods such as ISO 13314 or other ASTM standards, which are very similar as well. Over to the other side, obviously the classic one that everyone hears about is improving osseointegration from porous structures. So we can look at providing good fixation for a bone graft, and we need to do that by identifying the correct pore size that's needed for the internal porous structures. And what's interesting about this is once we start to do this, we start to move into requiring very fine strut sizes, which requires us to refine our laser parameters, which shows that close link between our product development cycle and our process development and our process optimization. So once we have our design envelopes defined, we can start to actually get into the fun of developing the product which meets those. So you can see here that we've got multiple geometries for our porous structures. And what we're trying to do with these is with two key requirements. One is to control the mechanical compliance, which is defined by the equations you see in the middle, relating the density of the porous structure to the mechanical properties. And the other is to specify the specific specific pore size to optimize for osseointegration. And what this allows us to do, once we're able to define our key requirements in a mathematical form, we start creating this link between the required product performance and the physical shape of our final product. We can feed these equations into parametric softwares and really speed up that iterative design process. And you can see here some of the key cell geometries that we've gone forward with for our development. So we can now move into our design iteration phases. So you can see a few of our concepts which made it to the late stages. And while there's a lot of differences between them, they're trying to hit on the same key requirements. We have some method of initial fixation, be those ribs, teeth, or the inclusion of pedicle screws. We have large-scale compliance mechanisms in them. So you can see the recesses or even cantilever features which are coming into the product. And we also have large internal voids which are concave in shape. The concave shape allows us to produce these with no supports, and it also maximizes the space that we can pack bone graft inside. Also, they're all sharing this bullet nose tip, which I mentioned earlier, to allow them to build straight onto the build plate. When we look at the lattice structures, we have two main functions of the lattice structure. We've got features on the top and the bottom surface of the part, and these are to promote osseointegration. We want to get that bone to grow into us as quickly as possible, and we've specified the optimal pore size for that, between 0.2 for wicking of osteoblasts and 0.9 for full bone ingrowth. And then finally in the middle, we've got a mechanism for allowing compliance, be that through a large-scale feature or the lattice structure. And an important one here is we want to use a stochastic structure, a random structure in the middle, to minimize any potential shear planes which could exist throughout the entire structure. Next slide, please. So now that we have some final concepts, we're able to develop these out in our traditional CAD softwares. You can see some of our final concepts here. Again, sharing quite a few similar methods. We've got porous features on the top and bottom, stochastic features in the middle to allow for that compliance. We've also got the inclusion of pedicle screws on the left-hand side to allow for that initial fixation, and then teeth and rib features on the right-hand side to do the same. On the left-hand side, if you take a look at the large-scale voids which are inside, you can see a sort of chapel roof style design to them. And what this allows us to do is it means we can achieve the same functional void and gap within our device. However, we're able to produce it completely self-supportingly. This overhang feature, along with the bullet nose tip, we're able to quickly develop using on-machine testing to find out the effect of contact patch and surface overhang angle on the surface finish. And as much as I wish I could say it's simply Control P and we're able to get our final parts printing, we do need to go through an iterative development cycle. So looking here at the images, on the top, we see our development of laser parameters for stochastic structures of very fine struts. So here we're aiming for a strut size of between 0.2 and 0.3 millimeters. And you can see our DOE study that we're running here to try and optimize the laser parameters to hit those reliably and repeatably. You can see some structures performing better than others. And beneath that, you can see another study we're doing, which is looking at how we optimize laser parameters to improve that solid porous adhesion between the porous structures and the solid body underneath. And just there on the left-hand side, you can see some of our root cause analysis and defect identification that allows us to very quickly run through these systems. So with that, we're able to get to our final design, which I'm sure everyone's seen lots of images of being shared around. So on the left-hand side, you see our part finally produced. You can see those vertex center cubic structures on the top and bottom, and that compliant mechanism at the bottom. And you can see that there compared with the model developed in platform on the left-hand side. And you can see how closely those structures are matching. And then we're able to get to our final build design. Using our Renishaw AM500, we're able to produce 150 parts on our single laser machine. That takes place over 24 hours. On the quad laser machine, it's running down around 8 hours. And you can see some of the sample test coupons, which would be included in this. So we've got powder coupons, solid chemistry, and hardness coupons. And these are absolutely vital for ensuring your quality management system has the correct data that it needs. And you can see here the entire system is produced without support structures on the implants. So that's my spot, guys, and I'd like to thank you, and I'm going to hand you over to Chris.
Thanks, Mark. And Topology's mission is to enable engineers to design and ship high-performing parts in as little time as possible. With the computational modeling platform that is the NTOP platform software, users are able to leverage its capabilities for design, simulation, and advanced manufacturing. Through the use of robust and reusable workflows, engineers can enable advanced and high-performance geometries in an approach that unifies design, simulation, and manufacturing together. By integrating these workflows into their engineering toolchain, users will find that they can automate processes, eliminate software inefficiencies, and be more productive, while still maintaining integration with their legacy systems. The design approach of the ACID spinal device is very much a volume-based approach. Now, using the solid bodies provided in their 3D model, the designers over at IMR were able to assign certain bodies as solid regions and others as design regions to be populated with a lattice. By recognizing the regions as separate entities, the designers can be sure that they are working exclusively within their net shape and combining them at a later time only when they are ready to do so. One of the benefits of using the NTOP platform software is the ability to quickly and effectively sweep through parameter sets just to see how the geometry will respond to these inputs. From there, the designer is empowered with real-time feedback to make the best engineering decisions. To showcase some of this feedback, I can jump into the software and sweep through a few values for the pore size of these randomized lattices. In only a few seconds, I'm able to immediately assess what those inputs will yield and continue in the right direction from there. A key value of NTOP platform is also being able to easily reuse these workflows regardless of any changes in geometry. In the case of the ACID spinal implant, even if the input geometry set is slightly wider or slightly longer, the workflows are robust enough to compensate for these variations and continue to execute as intended. This alone has significant implications for spinal devices, which can have part families ranging from 20 parts to over 100. Being able to design a single robust workflow and reusing it over and over again has the potential of eliminating an exorbitant amount of repeated work when compared to a design process that needs to be tailored to each and every single implant. What is also recognizably important to these design workflows is their repeatability and controllability. Any workflow that is created in the NTOP platform software is not only PLM compatible, but also highly shareable. During the development of these workflows, only the variables that are relevant to the design exploration are modifiable. The rest of the knobs and dials that can introduce variability into that workflow are locked away so that the mistakes can't be made and the risk is greatly reduced. This enables a single workflow to perpetuate within a team or far within an organization while still adhering to the initial design intent. Finally, NTOP platform allows your geometry to leave the screen and become a physical product through one of two ways. The first is your classic mesh output, such as an STL format. These files are universally recognized, but can be a bit heavy when it comes to the file size, especially for lattice-based designs. However, we can take things a step further and bypass these heavy STL files by slicing the part directly within NTOP platform. By working directly with Renishaw, we've ensured that the contours and slices that we generate in the software can be directly read by Renishaw software, eliminating the pain points that come along with working through these traditional meshes. Now, I'd like to introduce Chris Stimmery from Renishaw to discuss the hardware involved in making the ACID device possible.
Thank you, Chris. So this is Chris Timmery from Renishaw Medical Dental Division. I'd like to give you an overview in terms of the features that are available on the Renishaw platforms and how they're relating to what Mark's doing at the IMR in terms of development for medical devices. Some of these features are going to span across R&D, also production of the devices. So if we could go to the first slide, please, Chris. Right, so Renishaw is producing, when we look at the software, our own software packages. So we've got a material editor. When Mark had touched upon the design of experiments that he was carrying out, he was very interested in having an open software source that was able to give him flexibility in terms of developing his devices and not constraining him at all. So Renishaw provides that solution here. There's over 150 configurable process parameters, and also one key thing is the laser is able to be used in continuous or modulated waves. What that delivers to you is the ability to actually melt metal at a very quick rate for, say, the very dense areas of the geometry, and then also use the modulated wave when you're looking at the fine lattice. So again, you've got complete open flexible development parameters. If you go to the next slide, please, Chris. The quantum build preparation software, again, developed in-house, so future developments, which is really important in this sector at the moment because everything's moving so quickly, are going to be delivered through to you as a user. Very easy to use, and again, gives you that wide flexibility. If you go to the next slide, please, Chris. So the 500Q machine is the latest machine available from Renishaw, and that was mentioned on a couple of occasions by Mark. An approximate build rate was about 8 hours for the plate of spinal cages that we were looking at earlier. The key point, 4 lasers are available within this machine platform, which is typically the size of a single laser machine. So you've got commercial and operational benefits there to the features that are unique to Renishaw, but then also technically there's been lots of improvements within this system as well. If we go to the next slide, please, Chris. So when I touch upon the technical advancements, what we've got is within Renishaw, we've designed our own galvo mounting system for the lasers. So that's actually the image that you can see there on the screen in front of you, and that gives us great control over the lasers themselves. And the key point which links in with the productivity and the operational side is that it allows you to get the 4 lasers output level in the footprint of a single laser machine. If you go to the next slide, Chris. Just looking in at the lasers and their configuration, how they operate typically in the marketplace at the moment is you have one configuration here on the left-hand side, which is a dual laser machine, and each laser is looking at approximately 55% of the bed each with an overlap region shown in the middle. Over on the right-hand side, you've got a full laser machine which can overlap also and has a gas flow which is downwards from the top of the machine and out to each of the corners. The Renishaw system has the ability for each laser to go to the full extremities of the plate. So you again have open control and flexibility to program the lasers to fire at any part with any parameters you choose to do within your device and manufacture process. So that eliminates the overlap regions. So that again gives you more flexibility, and potentially with some devices would mean that you can produce quicker. One of the key developments that we're bringing to the market with the 500Q machine is the improved gas flow. What that essentially means is that you get a better quality of metal being sintered from the machine. So you're getting increased mechanical properties. If you look down on the left-hand image, you have a laminar flow of air going across the bed. That was typical of what was the configuration on the previous machine designs from Renishaw. What we've also done in this machine is increase the flow, and then if you look up on the right-hand image, you've also got a downdraft coming from where the optics are from the top of the chamber, and that makes the whole chamber more efficient, gets rid of all of the unwanted particles which is happening in the process. So that means you get basically less inclusions within the material. When we put that into tangible numbers, you could be looking at potentially 19% elongation with titanium, some of our tests have shown. So yeah, there's lots of options available here for use, whether you're looking from a technical perspective, research development of devices, or also operation commercial aspect as well. So that's everything from me. I'm going to pass back to John now.
Next steps. So folks, if you've seen anything you like today and want to contact us for more information, we'll start with Entopology. Shoot us an email, sales@entopology.com. We are active on our blog. We have several going out all the time. Go to entopology.com/blog to either sign up or just keep a pulse of what we're putting out there. And we're also advertising future webinars like this at our homepage, entopology.com. If you'd like to learn more about Renishaw in particular, I think there was a written case study on this very topic. You can go to renishaw.com/spinal implants to read more about that, or contact Chris Dimery, who just spoke a moment ago, at chris.dimery@renishaw.com. At IMR, you can go to imr.ie. Don't go to imr.com. I made that mistake once. It is, in fact, .ie. And if you want to get in touch with Mark Hartnett, you can see his email address down there. So let's turn it over to a couple of questions. I know several have come in. Chris, and Mark, if you want to just jump in and start answering some of these, feel free to do so. Maybe I'll prime the pump by throwing one out there. Chris at Renishaw, this might be more relevant for you. The question was, in Renishaw's material editor, how do you apply multiple parameters to different parts of the part geometry?
Well, what I'll actually do, John, is if I pass this over to Mark, because he's actually doing this out in the real world, so he'll give you a better view from there, if you want to come in on that, Mark.
Yeah, absolutely. So in terms of assigning multiple parameters, it's really as simple as once you import your geometry as multiple bodies. So in our case, we were able to import the solid body as a single part, and then each of the porous structures as a separate body and maintain their alignment. We're able to provide independent laser parameters to each one of those bodies. And there's some work going on here to even go a little bit more in depth and go have some greater laser control. But from a production point of view, it is that easy as assign the laser parameter to multiple bodies and just have that thought in your mind as you're going through the design phase.
All right, thanks for that, Mark. Another question was in regard to the ACID device. If you can go into more detail as to what that actually does in the human body. Maybe Mark, if you want to tackle that.
Yeah, absolutely. So the ACID device, it's a spinal cage implant. So this is used if you have a degenerative disease which is affecting your intervertebral discs, your spinal discs. And if you know of anyone unfortunate enough to go through a vertebrae fusion procedure, they'll use a implant like such as this. So in the procedure, they remove the spinal disc, which is a soft shock-absorbing material, and implant this device in its place. And what this does is this restores that height between the individual vertebrae, brings back comfort, relieves any pressure on the spinal cord or any of the nerves around them. And that's its first primary goal. And its second goal to that is to allow for fusion between both the top and bottom vertebrae. So this is designed specifically for the cervical region, so up around midway through your neck. The C5 to C6 vertebrae is where we looked at specifically for this one.
That is fascinating. Mark, another question in regards to this design. Approximately how many iterations did you go through before finalizing this and printing it?
So for us, there was a few different iteration stages. We had around 7 concepts, which were able to get to our final design stage where they actually went through a full design cycle to CAD. And then we went through several iterative stages. The solid body was very easy. Renishaw's standard parameters produced that extremely well. And we went through about 5 or 6 iterations to refine in the laser parameters for our porous structures and refine those in. So you're looking at maybe 5 to 6 full concepts and then 5 to 6 iterations. But the benefit there is we're able to produce those all on our simulated, I should say, production machine. So we know that any validation work we have to carry out in the future is going to be made a lot easier because of that R&D taking place in the production machine.
All right, very good. Chris Cho and Chris Dimery, if there's any questions you guys want to tackle, now would be a good time to throw those out.
I can see one here asking for videos showing the Renishaw machine building these spinal implants. I think if we could put a link up to the case study, that would actually show that there, because there's a video on YouTube that would be able to give some details there.
All right, great. Yeah, we could probably include that in a follow-up email to everyone. Mark, this is probably a question for you. How long did the project take in its entirety from start to finish?
So for us, start to finish, we're looking at about 6 months, and that's taking into account initial case of full design cycle for us, and also some mechanical testing on throughout the design cycle, right through to kind of what you see today, final press releases.
Mark, another question came in for you. These are very heavy on all the work you did. What sort of mechanical testing did you do? Maybe you could touch on that a little bit.
So we wanted to do some representative testing and specifically look at the porous structures for this study. So I should say these aren't the complete rounded testings that will need to be done. There's a lot more for a fully validated device, but our 2 big ones, we're looking at compressive testing of the lattice structures themselves, and that was done against ISO 13314, just a global standard for that. And then also we wanted to look at the interfacial shear between the porous geometries and the solid body geometries, and we were able to do both of those on site here.
All right, very good. We've got most of the questions answered. There's a few that might be better suited on an individual basis.
So I can see there's some questions here about mechanical properties, post-processing, heat treatment, and Mark, would you be able to touch upon that one? I can say that from my experience, heat treatment is still required to meet the orthopedic standards. The points that I was making earlier is that we've increased the mechanical properties off of the machine. Typically, heat treatment is still required. But if there's anything you'd like to add on that one, Mark?
Yeah, I definitely mirror what you're saying there. A lot of the standards are blatantly calling for heat treatment such as HIP to be carried out, and once it's in a requirement like that, there's no getting around it. Whether or not the material properties require it is another question, but the standards require it, so they're mandatory. Our one there.
All right, anything else you guys want to answer? We're just a little over time, but if anything seems appropriate, go ahead and jump on it now.
I can see one here. So final one here. How can other companies benefit from this project? Certainly get in contact with us, and the IMR, I believe, would be offering services of trying to help develop this and share their knowledge in this sector. So contact Mark, contact myself, and any of the guys at Anthropology to look at how we can share our knowledge in this sector.
Yeah, thank you, Chris. I think that's a good one to end on. We'll go ahead and wrap it up there. We're a few minutes over time. Thank you all for coming. We sure appreciate it. We hope you have found this beneficial and informative, and be on the lookout for an email from us to give you some follow-up next steps and a streaming recording of this. So thanks again, and have a great remainder of your day. Bye-bye.